Good day, I'm Norman Wahlberger. In our last video we introduced the idea of an anti-particle kind of analog in pure mathematics, right at the foundations when we're trying to set up integers. We introduced the idea that besides starting with nothing and something, we might also include something which we call anti-something. So if our something is represented by a simple mark on the page, then our anti-something is represented by an anti-mark, which is just a mark with a little bar over it. The same kind of bar that the physicists use to denote an antiparticle of a fundamental particle. So with this setup, we now have three sort of fundamental ingredients to build up various multisets. So we have a trichotomy now, as opposed to a dichotomy that we had earlier. Now, this is a development that really has a lot of consequences that we'll see. And it's particularly important for us in setting up the arithmetic of integers. Certainly what we can do directly is create the basic integers that correspond to these three ingredients. If we take nothing and put it in an M set, then we get what we call 0, or the empty M set, denoted usually with a circle or a 0 there. If we put the single mark in an M set, we get the number that we call 1. And now if we put this single anti-mark in an M set, we get a number that we're going to call -1. So then our -1, 0, and 1 are the fundamental integers that correspond to these three sort of elemental aspects of our fundamental mathematical reality. Now, it's important to note that we don't have to do this, that it might be that in some situations things are better modeled just by a dichotomy between nothing and something. If you're interested in a kind of a black and white situation, on and off, something binary, then it's perhaps more sensible to just restrict oneself to this story here. But when we're trying to do arithmetic, we'll see that it really is useful to have these three things around. So now we have three different types of numbers in this context. We have integers, represented by int, which consists of both natural numbers and negative numbers. So natural numbers include things like this that we're already very familiar with. These are primitive natural numbers. Now we have negative numbers, which are very much like these, except that they consist of anti-marks instead of marks. And we note prominently that the 0 or empty multiset is also an element of both neg and nat. It is of type neg, it is also of type nat. And then integer, well, that represents the combined type, where we're including things of this kind or of this kind. So here are all examples of integers. This is something in nat, this is something in both nat and neg, this is in neg, this is in nat, this is in neg. They are all in int, or all of type int. So the arithmetical domain of integers is fundamental to mathematics. And so now a natural question is, now that we have the objects that are going to be our integers, how do we set up arithmetic with them? So the fundamental operation is, of course, addition. And that's relatively simple because integers are multisets, and we know how to add multisets. We just do that by combining the entries of various multisets. But there's something a little bit extra that we have to say. So something extra happens when we're doing addition with integers that we don't have when we're just adding natural numbers. And that's having to do with this reduction or this simplification due to this fundamental relation between our mark and our anti-mark. We've agreed that if we have a mark and an anti-mark together in the same multiset, that they cancel. They cancel to give us just nothing. Okay, so here's some examples of addition of integers. So here is mark, mark, and here is mark, mark, mark. When we add them, well, we just get mark, 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 mark. That's a familiar addition of natural numbers. Here's a corresponding example using just negative numbers. So there's a negative number, there's another negative number. It's a multiset of anti-marks, another multiset of anti-marks. We just combine them in the obvious way to get the sum. So this would be -4 plus -2 is -6 in our familiar language. More interesting is when we combine a natural number with a negative number. So mark, mark, plus anti-mark, anti-mark, anti-mark. So what we do then is we first combine the two multisets in the standard way of combining multisets. We just put all of the objects into a single multiset. But at this point we are not finished because we have to reduce. Here we see both marks and anti-marks and we're obliged to cancel them. So we cancel mark anti-mark pair as well as another mark anti-mark pair, and we're left with a single anti-mark. And here's another example. There's a negative number, there's a natural number. We combine the ingredients, and then once we have the ingredients, this is just an intermediate stage. We still have to reduce, so we pair off marks and anti-marks, make them disappear, and we end up with just these 4 marks. And a special but important case, if we have, say, 2 plus minus 2, there's mark, mark, and there's anti-mark, anti-mark. We combine them, we get the multiset mark, mark, anti-mark, anti-mark, and then after we've done a reduction, we have nothing left over. So the end result is 0. We would say this is 2 plus minus 2 equals 0. Now I remind you that one of the advantages in the multiset point of view is that addition is no longer just a binary operation, because the act of dumping out containers into a single container doesn't necessarily just require 2. We can dump out 3 or 4 or more. So for example, we might want to add this integer with this integer with this integer and this integer. And there's no need for us to have brackets now prescribing the order. Right? We are allowed to add them all at once. You just dump all of the contents out into a big M set. So there's those 5 anti-marks, a single anti-mark, and a pair of marks there. We get this M set. It's not yet reduced though, because it has both marks and anti-marks in it, so we're obliged to make cancellations. So we cancel those 3 with those 3, and then we just get these 3 anti-marks and a couple of marks. Then we have to do some more cancellations, and we end up with a single anti-mark. So properties, well, addition is commutative and associative. Well, that's because M-set addition is. When we combine multisets, the order doesn't matter. And if we combine 3 or 4 or more, it doesn't matter in what order we combine them. We all get the same collection at the result anyway. And finally also, this particular empty M set plays a special role because it's the additive identity. Namely, if we add it to any integer m, we get m. Or in our more familiar notation, we would say 0 plus m equals m. So now we come to multiplication of integers, which is a little bit more subtle. But because we're talking about M sets, it turns out that we only really need to define our multiplication at the level of the objects which are ingredients of our M sets. Since we only have 3 ingredients, our mark, nothing, and our anti-mark, it's enough to say how those things multiply with each other. So here is now an extension of a multiplication table that we had in a previous video where I told you how to multiply mark and nothing by mark and nothing. Now we have to also include the anti-mark. Okay, so this table will be, I think, relatively obvious. If we multiply mark times mark, we're going to define that to be mark, while mark times anti-mark is going to be anti-mark. And commutatively, anti-mark times mark will also be anti-mark. The empty nothing times anything is going to be nothing. That way there's blanks here and here. The only thing that's a little bit special, really novel, is this entry here. We're going to define that the product of an anti-mark with an anti-mark is a mark. Not an anti-mark, but a mark. So this is a definition that we make, right? We could make any definition we wanted to, and we would then have a corresponding arithmetic. But it would be more or less useful depending on how reasonable our fundamental multiplication table is. So it turns out that this is really the best choice, as we'll soon see. So in words, we could say that the table is telling us that something times anti-something is anti-something. And also in the other order, anti-something times something is anti-something. And a novel one right here is that anti-something times anti-something is something. So you should think about this as being a definition that we're making. And it's maybe arbitrary. We don't need to justify it. We're just going to say, here is exactly what we mean by what an anti-mark times an anti-mark is. It's defined to be a mark. The usefulness of this will make it clear that this is a good definition. So once we have the multiplication of the ingredients, then the multiplication of m sets, in this case integers, just follows from the m set extension. So for example, if we multiply mark mark times mark mark mark, what we do is we create a new multiset which consists of all possible products of the entries here with the entries here. So we multiply this mark times that mark, that's a mark, and then the first one times the second, the first one times the third, and then the second times the first, the second times the second, the second times the third. We just go through all possible products between these guys, and we make an m set correspondingly. Here we have anti-mark times mark 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 mark. So as long as we know how to multiply an anti-mark times a mark, we're okay. And we know how to do that. Our basic multiplication table tells us that's an anti-mark. So we're going to have this product is an anti-mark, and then so is the next one, and the next one, and the next one, and then moving to this one, its various products will give us 4 more. So altogether there are 8 anti-marks there. If we multiply the empty m set by, say, this negative number, then we have to take the possible products of things in here times things in here, and the products are, well, empty times mark is always empty. So we get empty, 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 give us altogether empty. And finally, if we have this negative number times this negative number, we have to use the fact that anti-mark times anti-mark is a single mark. So when we multiply this first one times all of those, we're going to get mark, 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 mark. And then this one times all of those, another 4 marks. And then this one, another 4. And that's the total. So minus 3 times minus 4 is 12. So as a little exercise, you can show that the basic multiplication table is associative, that basic starting multiplication, that 3 by 3 is associative, and that it then follows that this integer multiplication is also associative. So it's a very efficient and simple way of, first of all, defining multiplication and sort of seeing why the fundamental kind of law is satisfied. Beginners in arithmetic often ask, why is it that a negative number times a negative number should be a positive number? It's not entirely clear. From our point of view, it's because we've defined it that way. But that kind of begs the question, why have we defined it that way? So why is it that anti-mark times anti-mark equals mark and not something else? Well, one good answer is because that it ensures that multiplication is actually consistent with our fundamental relation that a mark adjacent to an anti-mark should equal nothing, that we have cancellation or annihilation of the particle and the antiparticle. So let me explain why that is. So let's look at this example here. Suppose we look at 0 times minus 1. Okay, so here's 0, here's an anti-mark. We know that the product is 0. Suppose we reconsider this by replacing this 0 m set with the m set mark, mark bar. So in the course of a calculation, if we got something like this, we would reduce that to this. So although this is not officially an integer, it is a kind of ingredient or an expression that evaluates to an integer. Let's work with it temporarily. Let's suppose that we try to do multiplication with this replacement of 0 times our minus 1. So we have 1 times 1 bar. Let's see, I should put a 1 bar here. Okay, so the rule is definitely that 1 times 1 bar is 1 bar. But suppose that we didn't know what 1 bar times 1 bar is, so we're not sure about that. Well, what would it have to be in order that this be consistent with this? Right, we want this to be equal to this. So we require that what we're getting here instead of that question mark should be a 1, so that these two will then cancel to give us the 0 that we require. So consistency with our basic annihilation rule really forces the marked bar times marked bar to be the mark. And another example, or maybe an extension or more elaborate way of saying something similar, is because it ensures the distributive property of multiplication and addition. So if you have 3 integers, m, p, and q, then a basic property is that m times p plus q is equal to m times p plus m times q. And I'm going to let you convince yourself that this is a true fact, and that it does really, involve this particular fact. This has to be the way it is in order for this kind of distributive law to work smoothly. Now, of course, one of the main reasons for having integers is so that we can also have subtraction as a key operation. So how do we introduce subtraction into the story? It's very simple. We define m minus n to be m plus minus 1 times n. So there's our minus 1, which is the m set consisting of the anti-mark, or mark bar. So for example, if we have mark, 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 minus mark, 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 in other words 3 minus 5, then that's the same as 3 plus minus 1 times the 5. There's our 3. We know how to multiply this m set with this m set. We get the m set of 5 anti-marks. And then when we add these two, we just get anti-mark, anti-mark. In other words, minus 2. Okay, so now you can verify some basic fundamental laws of arithmetic involving subtraction. If m, k, and n are integers, then m times k minus n is m times k minus m times n. Then m minus k plus n is m minus k minus n. That m plus k minus n is m plus k minus n. And that m minus k minus n is m minus k plus n. I guess this one here is a little bit problematic sometimes for young people. So what's involved here implicitly is a kind of a symmetry. We really have a symmetry between the natural numbers and the negative numbers. And it's encoded by this multiplication by minus 1 here. So we could give that a name. We could say that minus 1 times an integer n is minus n. Okay, that's what we mean by minus n. It means we're multiplying by this minus 1, which is our m set consisting of our single anti-mark. So this is a fundamental symmetry which interchanges nat and neg. Call it negation. And we'll see that it has a lot of consequences, this symmetry between the positive and the negative. So I hope you can appreciate that the framework that we're setting up here is pretty simple. That things really kind of fall into place because we're working in a familiar m set kind of environment, and we know how to add m sets and multiply m sets subject to our basic sort of understandings. So it's quite a pleasant kind of situation, and it's nice that there's really only these 3 fundamental ingredients. The ingredients of the mark on the page, the empty page, and the mark with a little bar over it, the anti-mark. And of course the multiset framework. That's another key ingredient, this idea that we're able to organize our data by using the idea of a multiset, something which is unordered and in which repetitions are allowed. So we really have now quite a solid foundation for arithmetic, because integer arithmetic is absolutely a fundamental kind of building block for mathematics. And let me emphasize that there has not been any games with axioms or assumptions or religious belief systems or incantations. Right? We're not proclaiming that something out there exists that we can't get a hold of. We're being very concrete. This is what you write down. This is an example of that. This is exactly how you add or multiply or subtract things. We can illustrate what we're doing very explicitly and concretely in a way that everybody can follow and then end up answering the questions in the same way. But there's no religious assumptions here about things that are beyond our view and that may exist or not. There's not even any discussion about existence. We're just talking about things that we can write down, computations that we can make, that we can exhibit concretely and explicitly. We're going to see that this trichotomy really opens up all kinds of new doors for us in terms of understanding lots of things in mathematics. In particular, the linear algebra kind of ideas that we were working with, having to do with maxels and pixels, and also vexels. We're going to see that we can now look at those things in a bigger, broader light with our view now of having integers as a tool for building up mathematics. It's very exciting and it will be kind of mind-opening for you, I hope. That's what we'll do next time. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.